Hello, everyone. Another session, and today we discuss Module 6 of CCNA 3, Enterprise Networking, Security and Automation. We take a look at network address translation for IPv4. So basically, what NAT is, and maybe let me define it by its primary use. It was used to conserve addresses. I think in previous levels, I think CCNA 1, we discussed the depletion of IPv4 addresses. And one of the main purposes of NAT was to help with the conservation of conservation of those addresses. So, and basically what it does, it translates to private IP addresses to public IP addresses. It's as simple as that. It can also be very useful with respect to security. With it, we'll be having a layer of security between the private and the public network. Um, Main objectives here will be to explain the purpose of NAT and the function of NAT, explain the operation of the different types of NAT that we have, static, dynamic, and PAT. Then describe advantages, disadvantages of NAT, configure static, dynamic, PAT. Then lastly, describe NAT for IPv6, which is NAT 6.4. Characteristics: IPv4 address space. Networks are commonly implemented using private IP addresses. They cannot be routed over the internet. We need public IP addresses for that. To allow a device with a private IPv4 address to access devices and resources outside the local network, the private address needs to be translated to a public address. NAT provides the translation of private addresses to public IP addresses. So you realize that private IP addresses, um, they're intentionally blocked from being forwarded to the public internet. We have McClassism addresses edu, where we identified private IP addresses. I think mostly we're dealing with these private IP addresses, 192.168. I think the prefix we've been using all along. The reason why we were using those addresses is because they are private IP addresses. It's because that is what we configure our private local area networks with. But when we are now talking of addresses that are able to be globally routed, we now talk of public IP addresses. You cannot globally route a private IP address. So you realize that in a network that connects to the internet, you need public IP addresses. So our private IP addresses will need to be translated to public IP addresses. Private IP addresses, internal network, public IP addresses, the internet, basically. The translation, that is what NAT does. A NAT-enabled router basically translates those private IP addresses to public IP addresses. What is NAT? I think we've basically defined it. Its primary use is to conserve public IPv4 addresses. It allows networks to use private IPv4 addresses internally, translates them to a public address when needed. Typically operates at the border of a stub network. What's a stub network? I think very important. From the diagram, we can see an example of a stub network. A stub network is basically a network which has one exit and one entry point. That's a simple definition. So for all stub networks, not all stub networks, for stub networks, You have a NAT enabled router at the boundary of the network. Everything that is coming from this internal network, uh, the NAT enabled router will translate all those addresses to a public IP address. So in the public address space, you can see we have a public IP address for our server there. So if PC1 wants to communicate with this address, this private IP address will not be able to be routed globally. So this router will translate this address to something that is public. Example 201.165.200.5. That's a public IP address. So this translation is what this NAT enabled router does. And that is basically what it defines what NAT is. How NAT works. So we're going to explain how this one works by looking at, we can see this PC with the private IP address. This is our server with the public IP address. So that means this is our NAT enabled router. This is our stub network. Step number one, PC sends the packet address to the web server. So if PC1 is sending a packet address to the web server, taking note of what the destination and the source addresses will look like. You realize that with NAT, we have two types of addresses. We have what we call the inside local, inside global address. From a perspective of the internal network, from our private network, with the inside local being the address of our device is seen from inside the network. So from inside the network, this is our address. That is what we call the inside local address. Then how do we see this PC from outside the network? From outside the network, we see the inside global address. So if this server wants to communicate with our PC, the address it sees is this one, the public IP address. What NAT does is to convert this address to this address, basically. This is what NAT does. So following our steps, R2 receives the packet, reads the source to determine if it needs translation. It adds a mapping to the local of the local to the global address, sends the packet with the translated source address towards the destination. So basically, what's happening here, if I send a packet from this device, this is the source. As soon as this packet arrives at our NAT-enabled router, this address is translated to a public IP address. This is the public IP address it is translated to. Then from there, when our packet is leaving to the destination, what will be its source? Its source will be 209.165.200.226, which is our inside global address. When our packet leaves this PC, its address source is 192.168.10.10. That same packet, when it leaves this router, this will be the source. So NAT is basically the translation between this private IP address to this public IP address. When the web server responds with the packet address to the inside global, R2 receives the packet with destination address. It checks the NAT table, finds the mapping, and then translates back. So if this server is now responding, what happens? Its destination, even if this is the final destination, you realize that the destination address will not be this private IP address. The destination address will be this one, the public IP address. So it responds to this. Then there will be another translation back to the private network. Then that's how we get our response from the server. So in short, I think it's evident how NAT works. It basically translates our inside local address, which is the private address, to an inside global address, which is the public address. The type of addresses that we have, I think we've basically defined these two already. The inside local address, that's our private IP address. The inside global, that's our public IP address. Then the outside local address, That's our destination. That's the destination address. Then the outside global address, that's also the destination address. But if I take a look at this example, so from perspective, yet destination here, this is our destination. From perspective, yet destination here, the outside local address, this could be the same as this one, a private IP address. Only that in this case, this is a server on the internet. So you realize that this address in this one is the same. The outside local address and the inside local address are the same. But to understand what those two addresses are, I think I might give an example like this. So let me say I have two networks like this. So let me have PC1 here. Let me have PC2 here. So I have two private networks that I have. Then I have 192.168.10.10. Then I have 192.168.20.20. Let's say this is the internet instead of this router. Let's say we have the internet right here. So these are two devices which are communicating over the internet. So from this perspective, if we are sending our packet from PC1, this address is our inside local address. Then let's assign a 165.10.20. This will be our public IP address. So this is our inside local, this is our inside global. From perspective of the destination, this is the outside local. Then we can have an outside global, 202.165.10.10. So if I'm sending from this end, we have these two types of addresses, and our destination will be looking like this. The outside local being the private network, the outside global being the public IP address of our destination. In the example that we have here, I think the tricky part is that these two addresses are the same. And the reason why they are the same is because this server is, it has a public IP address. It has a public IP address assigned to it. It does not have a private IP address, which is then being translated to a public IP address. So inside local, inside global, outside local, outside global, by their definitions, the outside address of the destination, the global address that appears on the outside portion of the network. I think that's very straightforward. Right, let's have another example that defines the type of addresses that we have. Inside local address of the source is seen from inside the network. So inside local, that address is seen from inside the network. From inside the network, this is our IP address. That's our inside local address. Inside global, address is seen from outside the network. If we are looking from outside the network, what is the address of PC1? From outside the network, the address of PC1 is its public IP address, not the private. So the inside global address is the public IP address of PC1. Then the outside global address, that's our destination, is seen from outside the network. So if we are looking at our destination from this side, we'll be looking at its public IP address, basically. In this case, destination, let me see. In this case, our destination, I think that's the address. Inside global. I'm looking for the outside global, outside global. Voila, that is our outside global. It's the address of this web server. Then our outside local, that's our destination, is seen from inside the network. I think it's basically the opposite of this. inside local, inside global, a scene from inside the network, or a scene from outside the network. Then here we're talking from a perspective a source. Here we're taking from perspective a destination. If our device has a public IP address, you realize that the local and the global address is the same, which is basically the public IP address. All right, type of network address translations that we have. We have static, we have dynamic, then we have port address translation, PAT. With static NAT, here we basically have a fixed one-to-one mapping of the inside local and the inside global address. Static NAT is useful for web servers or devices that must have a constant address and that is accessible from the internet. It is also useful for devices that must be accessible by authorized personnel when off-site, but not by the general public. So what static NAT is basically is a one-to-one mapping. What do we mean by that? If we take a look at this is our inside network, this is our private network, basically. 3 devices that I have, this server and these 2 PCs. For me to communicate globally from these devices, this one will need its public IP, this one will need its public IP, this one will need its public IP. So that's where the one-to-one mapping is. For every private IP address that I have, for every host that I have locally, then I will need a public IP address for that specific device. In this example, you can see 3 private addresses, 3 public IP addresses as well. Useful for web servers or devices that must have a consistent address that is accessible from the internet. Static NAT is very useful, especially for configuring my servers. The reason why is because, let's say, for example, from my private network, I need to access a server over the internet. Let's say a web server over the internet. There is a consistent communication that is required, consistent connection that is required with that web server. So a one-to-one mapping allows us to consistently connect to that web server. When we discuss dynamic NAT, for example, you're going to realize there is no consistent addressing with dynamic NAT. At one point, you can have address, public IP address A. At another point, you can have it as B. It changes. So that's no longer consistent. But when you need a connection to a server, which must be consistent, static NAT is the way to go, basically. And how you configure it, I think configurations will come soon after this. Static NAT, one-to-one mapping, simple. Dynamic NAT, it uses a pool of public IP addresses and assigns them on a first come, first served basis. When an inside device requests access to the outside network, NAT assigns the pool. NAT assigns the available address from the pool. The other addresses in the pool are still available for use. So with dynamic NAT, we have public IP addresses being assigned on a first come basis. We have a pool that we have. Then if a private IP address, if a device is trying to communicate publicly, it will be assigned an address from the pool. Like already said, on a first come, first serve basis. In this case, the size of the pool will need to be large enough to accommodate all the connections from inside from the internal network, basically. So in short, what we have, instead of having a one-to-one mapping for all these addresses, what I have is a pool. I create a pool of public IP addresses. If this device wants to communicate with the outside network, it gets assigned a public IP address. If another wants to communicate, it gets assigned another one. It gets assigned another one. So to some extent, it might seem like it's a one-to-one mapping, but it actually isn't, because we are saying you get a public IP address from the pool only when a connection is needed with remote networks or a connection over the public network. You can see as well, if, for example, here we have a pool with 1, 2, 3, 4, 5 addresses. If we have a pool with 5 addresses, it basically means we can only have 5 connections at a time. If we have a 6 connection, six device trying to connect to the public internet, and all these sessions are still open, then what it means, this one will not be able to communicate because it will not be able to get a public IP address. So the importance of this is basically we must have sufficient public IP addresses in our pool to accommodate all the devices or excuse me, all the multiple connections that will be requested from our internal network. Difference between static and dynamic, you realize that dynamic is a bit flexible in the sense you don't have to manually configure one-to-one mappings. You can only create a pool, and every device trying to connect will get an address from that pool automatically. You then have to map every address in the network to its public IP address. Difference between static and NAT as well, you realize that with static, you can have connections, inbound or outbound connections. So with static, let me say PC1, this is our internet. Then we have our server here. With static, there is a one-to-one mapping between the private and public IP address. If I want to communicate with the server, this is what we call an outbound connection. It's possible. If the server wants to communicate with this PC, that's an inbound session, it's also possible. The reason why it's possible is because there is a consistent connection between this PC and this server. Why? Because of the one-to-one mapping between this PC and its public IP address. This does not change. You can manually change it, but once you manually configure your mapping, then it means every time this PC is trying to connect to the server, it uses this specific public IP address. It also means that if this server wants to communicate with the PC and it uses this public IP address, then it means it's going to this PC. The difference now with dynamic, with the dynamic, we have PC1, we have our internet, then we have our server here, and we have a pool. Let's say we have addresses A, B, C in our pool. So if PC1 wants to communicate with the server, it might get assigned this address, then it communicates with the server. And if the server responds, it responds to this public IP address and it goes back to the PC. However, if we have an inbound session, initial session coming from this server, we might have a problem of this server probably not, let me put it this way. Let's have another PC2 first. Let's have another PC2 first. So as I said in the first session, PC1 is trying to connect to the server. It gets assigned this address. That session ends. It means this address is now available. PC2 tries to connect. It gets addressed the same public IP address. Why? Because the session with PC1 has ended. So this address can be assigned to PC1, PC2, or even PC3, any host if it is available. That inconsistency means if this server tries to communicate first with any of these devices, it tries to communicate with this, at some point it might communicate with PC1, PC2, or PC3. Therefore, you cannot have inbound sessions with respect to dynamic NAT. Why? You never know where you land. With static, you always know where you land. Why? Because there's a one-to-one mapping between the PC and this public IP address. With dynamic, there is inconsistency there. If this address is available, it might be given to another host in the internal network. So the dynamic, there's a level of inconsistency there. I think that's a disadvantage for dynamic as compared to where are we in Africa? As compared to static. Right. Port address translation, also known as NAT overload, it maps multiple private IP addresses to a single public IP address. With PAT, when the NAT router receives a packet, it uses a source port number to uniquely identify the specific NAT translations. It ensures devices use different port numbers for each session with a server on the internet. So basically with this one, we have multiple internal devices using one public IP address. With static, if I have PC1 and PC2, there is a one-to-one mapping with public IP 1 and public IP 2. This is static. One-to-one mapping. With dynamic, if I have PC1, if I have PC2, I have a pool with addresses 1, 2, 3, 4. So I'm using multiple addresses if I have multiple internal devices. With PAT, port address translation, I have PC1, I have PC2. I only have one public IP address. All these devices, they use this one public IP address. So what separates sessions is now the TCP or the UDP port numbers. In this example, you can see these two devices are trying to communicate with, I think one of these servers or both of them. Our inside local address, you can see this is .10, so it's this PC. It is accompanied by the port number. There we have the port number. Then you see it will be translated to this public IP address. This is our inside global address. This device, .11, it also has the same public IP address. These two are the same. What's different is these numbers, these port numbers. So what will separate sessions with respect to PAT are port numbers, but the inside global address will be the same. Multiple internal IP addresses, one public IP address. What differentiates sessions is now the port numbers. That is basically what defines PAT. And like dynamic NAT, this one we cannot have outbound sessions, no inbound sessions. We cannot have inbound sessions. The reason why is the same reason with, can we have inbound sessions? No, we cannot. The reason why we cannot have inbound sessions is because of the inconsistency with the translation between the public and the private and the public addresses. I think I'll open up on when you discuss how PAT functions, we'll open up and see why we cannot have inbound sessions starting from the outside network. Next available port, right, with PAT, one of the problems we have with PAT is, let's say Let me read first. PAT attempts to preserve the original source port. If it is already used, it assigns the first available port number starting from the beginning of the appropriate port group 0 to 511 to 1023 to 65535. When there are normal ports available and there is more than one external address in the address pool, it moves to the next address to allocate the original source port. The process continues until there are no available ports or external IPv4 addresses in the pool. Right, so the problem with, it's not a problem, but with port address translation, like I said, we'll be using port numbers. We are going to have a problem when this device, it's using its source port, this one is also using the same source port number. So if I then want to translate here, it means both of them are going to have the same inside global address, this one. They are also going to have the same source port numbers. That's a problem. Why? Because we cannot differentiate those sessions. So with the next available port, what happens is whoever comes first. So if this PC requests first, it gets assigned this address with that port number. If this one also requests translation, this router will check this port number. It will see that it has already been used. Then it will select the next available port. So this is what we call dual translation. We have not only translated the IP, we've also translated the source port. Then if we are communicating from outside the network, we are responding. With this one, it gets translated directly back to these numbers, the private and the port number. With this one, it will also need to be converted, translated back to this address and this one. So it means we are going to change this to this, and this will also need to be changed to this one. Like I said, that's what we call dual translation. Here is not only translation of the IP address, it's translation of the IP address and the source port as well. Brief comparison of NAT and PAT. Only modifies IP addresses. So network address translation, it only deals with IP addresses. This one, it also deals with port numbers. With NAT, we have one-to-one mapping. Here we have one inside global address can be mapped to many inside local addresses. So with this one is one-to-one. With this one is one public IP address for many internal devices. Uses only IPv4, uses port numbers. Unique inside global address is required for each host. That's the one-to-one mapping. A single unique inside global address can be shared by many inside hosts accessing the outside network. Right. Another important thing, when we introduced network address translation, we talked of address conservation. If you take a look at static, do we have address conservation? The answer is no. Why? Because for every private IP, we have a public IP. So what are we conserving there? Because for every device that has a private IP address, we are going to map it with a public IP address. We are not conserving anything. So static NAT is not much about conserving. I think it's more to do with having a consistent connection, communication with a server that is outside the network. That's where it is very useful, not conserving IP addresses. With dynamic, are we conserving addresses? The answer again is no. Why? Because the pool, every address in the pool is going to be used by internal devices. So if I have multiple PCs and they need to communicate globally, if all these three need to communicate globally, then they are going to get all three addresses. They are going to get three addresses in the pool. We are not conserving any addresses that way. The only way we will conserve addresses is by using port address translation. Why? By the simple fact that multiple devices, all these three devices, they can use one public IP. That's where the address conservation comes in. So with static and dynamic no address conservation, with port address translation, definitely we have one. Packets without layer 4 segment. With port address translation, we have introduced the use of port numbers to separate sessions. But what happens if we have a packet which does not contain port numbers, which doesn't have the layer 4 information that includes the port numbers? Such type of packets, we have the ICMP version 4 packets. It does not have layer 4 information. So how then do you define the source port when you are using when we're dealing with port address translation? We don't have to use it. Here we use what we call the query ID. So these type of packets, they have a field which we call the query ID, which will be used in place of the port number. That's basically what that is about. Other ICMP messages do not use the query ID. These messages and other protocols that do not use TCP, UDP ports are beyond the scope of this curriculum. They are also beyond the scope of my brains. I don't know these type of messages. But anyway, this is up there. So we are basically saying we can use the query ID in place of the port ID. If we don't have the port numbers, we can use the query ID. NAT advantages and disadvantages. Advantage number one, address conservation. Is it NAT? It's PAT, but it's a form of NAT. So we have address conservation by allowing privatization of intranets. Increases flexibility of connections to the public network. What is this one? Flexibility of connections. Where is the flexibility? I'm not so sure about this one. Then with multiplexing, that's straightforward. It provides consistency for internal networks, network addressing schemes. So we discussed this one when we talked of static, we discussed of that consistency. So with static NAT, we do have that consistency. Allows existing private IP address schemes to remain while allowing for easy change to a new public addressing scheme. Okay, so basically, if I have a public IP, this can remain the same, don't change. Meanwhile, within my network, I can change everything here, but my public IP address will still remain the same. I think that is what they are speaking of here. That hides IPv4 addresses of users and other devices. That's the security part of NAT. So the public will not know the IP address of the private networks. What it will know is the public IP address after translation. So that's a layer of security that NAT affords. Drawbacks increased in forwarding delays. One of the drawbacks drawbacks. One of the drawbacks that we have there is um, delays. I think reduced latency, if we can increased or reduced. We have latency, a lot of latency, increased latency basically. Why? A lot of overhead. There is a lot of processing that is required to be done. When you are translating, that's processing. That's where the delay is coming from. When you want to translate back from private to public, when you want to translate the port numbers, that's a lot of processing. That's where I think the delays are coming from. End-to-end addressing is lost. Yes, why? Because there is translation. If I'm communicating with PC1, PC2, address A and B, this is end-to-end addressing. I'm communicating with address A and B. But with NAT, this address will be converted to X, this address will be converted to Y. So this is no longer end-to-end. That's where it's coming. And with that, we have difficulties in tracing, troubleshooting. It's very difficult to troubleshoot. Why? Because you're dealing with addresses that are translated, you're dealing with hidden addresses, hidden networks. That's a problem. Another disadvantage, it complicates the use of tunneling protocols, such as IPsec, services that require the initiation of TCP connections from the outside network, or stateless protocols, such as UDP, can be disrupted. Not sure about that one. Complicates the use of tunneling protocols. Why is it complicated? Probably, I think, something to do with this as well. Because for tunneling, we need this end-to-end addressing. Then the last one, those inbound connections. So with dynamic, with PAT, we cannot have sessions being initiated by devices from outside the network. The reason why is because my addresses from our internal network can change. So there's an inconsistency between the public IP address and the private IP address. You initiate a session thinking you are connecting to device A, however, you'll be connecting to device B. That's why we cannot have that's why we have disruption with respect to inbound connections. Inbound connections, connections from outside the network. That's a drawback. Now, configurations. I think this is more of a deeper dive to static NAT. One-to-one mapping, we've discussed that, allows external devices to initiate connections. This is the only type of NAT which allows external devices to initiate connections. So this one, that's an external device. It can initiate a connection. This one obviously can initiate a connection. Uh, this static NAT allows for that. We'll look at dynamic and we'll discuss why it doesn't allow as well. For instance, an internal web server may be mapped to a specific inside global address so that it is accessible from outside the network. That is a scenario for static. With respect to the configurations, how do you configure static NAT? It's basically three commands. Okay, it's basically three commands. Number one, you have to create a mapping. You have to create a map for every private IP address that we have. So in this example, we are mapping this private IP address to this public IP address. That's it. Using the IP NAT inside source static command, you map your addresses. Then from there, you define your inside and outside interfaces. What are the outside and inside interfaces? These ones, we identify them with respect to our NAT-enabled router. So in this case, this is our NAT router. These two interfaces define the interfaces participating in the translation. So from inside the network, we have the inside interface. Here from outside the network, we have the outside interface. So to configure these two, we just enter the interface configuration mode and you input the IP NAT inside or IP NAT outside command. Simple configurations, analyzing static NAT. Here we have the web server trying to have a connection with the client, or the client from outside the network trying to communicate with the server. 5 steps that we have. Step number 1, the client sends the packet to the web server. So our communication is going this direction. R2 receives packet from the client on its outside interface and checks its table. R2 translates the inside global address of to the inside local address and forwards the packet towards the server. So basically, steps 1 to 3. That's our inbound process, communication from outside the network. That's our inbound process, where our client is initiating a connection. And as you can see, our destination address from this client perspective, our destination address is the address of the public IP address of this. This is our destination address. 209.165.2015 is the public IP address of our destination. It's not this address which is here. It's the public IP address. So that's step 1. Step 3, I think that's our destination address now translated. So this one translates this address to this one. That's the translation part. Steps 4 and 5, web server receives the packet response. R2 receives the packet from the inside interface, then translates back. So this is our response. This is our source address, this address. For us to communicate with the outside network, this is a private address. It will need to be translated to a global address. Simple. That's how NAT, static NAT works. Verifying, we have show IP NAT translations and show IP NAT statistics. With the translations, as you can see, it shows, this command shows active NAT translations. So this is an active NAT translation. This is being converted to this. That is what the NAT translations show. If command is issued during an active session, the output also indicates the address of the outside device. So this is an active session, and this is an address of the outside device. So our active NAT translations, here we have one, inside global and inside local address. So this one is of the active session. In short, the show IP NAT translations basically provides us with information about the translations, the current mappings that we have, and the translations that we have. Show IP NAT translations. The other one, we have show IP NAT statistics. Like how it's defined, it gives us the statistics. You can see hits or misses. Hits is probably how many addresses have been translated. Misses, addresses not translated. So this one, it gives us information about the type of translations that we have. Example here, we have static, 1 static, 0 dynamic. Those are the type of translations that we have. Also giving us information about the statistics, what's the total number of translations that we have, what are the hits and what are the misses. Show commands, very important. I always say this. Moving on to dynamic NAT. What's our time? Moving on to dynamic NAT. Why am I still recording? Should this not end at 45 minutes? Okay, let's continue. Moving on to dynamic NAT. Dynamic NAT automatically maps inside local addresses to inside global addresses. We have creation of a pool. The pool inside global addresses is available to any device on the inside network on a first come, first served basis. I think we've gone through this. There is our scenario. Let's look at how we can configure dynamic NAT. Step number one, you define the pool. Number two, define an ACL. Number three, bind the ACL to the pool. Number four, identify interfaces on the inside and interfaces on the outside of which basically perform our translation. Right. So to configure dynamic NAT, step number one, you have to define a pool of addresses that will be used for the translation. So in this example, we've defined a pool. This is the pool name, IPNAT pool command. This is the pool name. Then our pool is basically addresses from 226 to 240. That's our pool. 226 to 240. That's the pool of addresses that we have. Then we have our net mask as part of our command. Step number two, configure a standard ACL to permit only those addresses that are to be translated. Our ACL will define addresses that needs to be translated. In this example, you can see all addresses in this network, 192.168.0.0 are allowed. So those are the addresses that will be permitted to get addresses from this pool. So basically what we are doing, we are saying, let me see, 192.168.0.0. Okay, they've combined these two networks, this network and this network. That is what gives you 192.168.0.0.0.0.255.255. A combination of those two networks is what gives you this network and wildcard mask. Now, basically with the commands, what we are saying permit these addresses to be translated using addresses from the pool. That is what we are saying with command number one and number two. Then command number three is basically binding the addresses that we are permitting, the traffic that we are permitting to be translated, we bind it with our pool. And basically that's it. Step 4 and 5, I think this is common for all the type of NAT configs that we have. You have to define your interfaces, the inside and the outside. Simple. Analyzing dynamic NAT. In our example here, we have, how many steps to H6? We have PC1 and 2 sending packets, requesting a connection to the server. So PC1 and 2, they want to connect to the server. R2 receives the first packet from PC1, checks the ACL to determine if the packet should be translated, selects an available global address, creates a translation entry in the table. So with dynamic NAT, we have a pool, we have a command which permits or denies translations. So if PC1 wants to send information to the server, there is our source address. If it is allowed by the ACL to be translated, it will be translated to this public IP address. This public IP address is chosen from the pool. Where is our pool? Inside global, inside, there is our pool. These two addresses are part of our pool. So this address was the first one which was chosen to be picked with respect to our PC1. Then with PC2, if PC2 now tries to communicate, it will get the other remaining public IP address. If we add a PC3 here and it tries to communicate, there will be no communication. Why? Because we do not have a third address in our pool in this case. Steps 4, 5, 6, I think it's just a response. So the first one, that was an outbound session. In this one, that's a response to our outbound session. So basically, it's translation as usual. The global addresses are being translated back to the local addresses. I cannot repeat this. Show commands. Here we have show IP NAT translation verbose. So the keyword displays additional info about each translation, including how long ago the entry was created and used. So this is a command which has some extra information with respect to the show IP NAT translation. So it gives you an idea when the entry was created and when it was used. Can I see that? When was it created? Is this not time? This is not, this is time as well. When it was used, when it was created, what is left? I'm not so sure of this. But basically that is part of our show IP NAT translation verbose command. We also have the IP NAT translation timeout. By default, translation entries timeout after 24 hours, unless the timers have been reconfigured with the NAT translation timeout. So by default, in an example or with global, in an example with dynamic NAT where we create a pool, PC1 gets an address from the pool. After 24 hours, that entry times out. It means PC1 will need to connect to the pool and get a public IP address again after the time. So we can manipulate that the time on that timer using this command. You can change how long do you want an entry to be timed out. Clear IP NAT translations. What does that command do? With clear IP NAT translation, it's basically it clears everything. It clears all the entries that we have on our NAT translation table. That's another show command showing us statistics. Don't think there is much there. Show running configurations. So show run can gives us an idea of how we have created our NAT. So this is dynamic NAT. We have created a pool and we have tied that pool to ACL number 1, basically. That is what the show run is showing us. PAT. PAT, it's the configurations, they are sort of the same with the configurations for dynamic. One, you have to, okay, define traffic. Define traffic to be translated. That's number 1. So to define traffic that needs to be translated, this is where we use our ACL. So this one is the same as dynamic. Then 2, you need to define the public IP address which these addresses will be translated to. So you can either use an interface or you can use a pool to define the public IP addresses. So this defines the public IP. Then number 3, obviously, as usual, you define your interfaces inside or outside. Now, when we are using a single IP address, this is the same as when we're using an interface. How do I put this? So there are 2 ways basically of configuring paths. The first one is by using the interface. Example, let's have our network. So let's have PC1 This is our NAT enabled router. Then we have Gig Ethernet 01. Then we have Gig Ethernet 00 on this side. So this is our internet. Then this is our server. Let me have PC2 as well. Right. With the interface-based part configuration, basically what we are doing is we are going to use this interface, its public IP will be used for all the devices in this internal network. So basically, if PC1 wants to communicate with the outside network, it's going to use the address of this interface. If PC2, it is also going to be using the address of that interface. So the exit interface, the outside interface, its IP address will be used as the address for our global address. So in this example, if we take a look, I think we're using this diagram. It's the same diagram topology we are using. Let me go back. This topology. Suppose there are no interfaces though. It's not the same topology. Where is it? Right, let's use this one. So with the first type of configuration, it is going to use this IP address. This is the address which will be used for the for translating every private IP address here is going to use this IP address. So the command goes access list 1 permit. So this is where we are defining the traffic. This is step number 1. You define the traffic that needs to be translated. Then step number 2, we go directly to binding. So this is where we are binding the traffic that needs to be translated with the source list 1 and the public IP address that's going to be used, which is an interface IP address. Here, these are our NAT inside and outside, defining our interfaces. The other way of doing it is by defining the pool. So this one is now almost exactly the same as dynamic. The only difference is this keyword. So the same with dynamic in the sense, one, we create a pool. However, that pool at times will only have one address which is being used. Why one address? Because this is port address translation. Many private IP addresses will be using one public IP address with sessions being separated by port, TCP or UDP port numbers. So like I said, number 1, define the pool. Number 2, define the traffic that needs to be translated. Number 3, this is the binding part. Bind your ACL to your pool. With the previous command, we bound our ACL with the interface instead of the pool. Then these ones, the common commands, define your interfaces, your inside and your outside. How does part work? Analyze part. So here we have PC1 and 2 sending packets to server 1 and 2. Packets from PC1 reaches R2. R2 modifies, translates to a public IP address. Packet is then forwarded to server 1. The packet from PC2 arrives. PAT changes the IP address to the public IP address. PC2 is the same source port number as PC1. If two PCs have the same source port number, what happens? We use the next port number. I think that is what we have here. So this is our source and source. This is our source and source. Our port numbers here are the same. For our global addresses, you can see this source and this source, the IP addresses are the same. That is what defines PAT. However, These ones will be different. This one is the same as this one because it was the first one which was chosen. This one is no longer the same. Why? We chose the next one. Now we have 1445. Step number 4, the servers use the translated addresses in port for destination. Server replies, server replies, server replies. So what happens with the responses is translation as usual. I think the only trick part with this one is understanding that there will be dual translation. This one will need to be translated back to this one basically, so that we use the original source port instead of the one that was translated. Not much here. Verifying part, we have show IP NAT translations, NAT statistics, we've gone through that. Then to end, we have NAT for IPv6. NAT for IPv6 is not for address translation. It's a bit different from IPv4. With IPv4, we are translating private to public IP addresses. But logic is saying to me, with IPv6 addresses, every host is assigned two addresses. This one is for local communication. This one is for global. So if every host is assigned two addresses, what's the need for translation? Because the device already has two addresses, one for local, one for global. So that said, I think you get why NAT for IPv6 doesn't speak to address translation. Instead, it's more inclined with protocol translation. If you're communicating between two protocols, IPv4 and IPv6, NAT64 will be used to translate IPv4 traffic to IPv6. Very useful in tunneling, by the way. I think basically that is what NAT64 is, nothing much here. With that, we conclude our session. In summary, what you need to understand. What you need to understand is, number one, we have this type of addresses, inside local, then we have inside global, outside local, outside global. This one is private. This one is public. We have static, dynamic, port address translation. This one-to-one mapping. This one, a little bit more flexibility. We have a pool. These two, no conservation of IP addresses. This one, many private addresses can get one public IP address. We have conservation of addresses. These two, no. This one, we can have inbound sessions here. Sessions initiated from a device from outside the network. With these two, you cannot have inbound sessions. We cannot have sessions initiated from outside the network. Why? Because address mappings between the private and public IP addresses change. It changes. Therefore, you cannot know for sure from outside the network what the public IP address you're communicating with translates to on the inside network. I think I've said a lot. Thank you very much for taking your time going through with me network address translation. On to the next one. I'll let out.